Okay, section 6.1. 6.1 is areas between curves. Okay, the area A of a region bounded by the curves y equals f of x, y equals g of x, and the lines x equals a and x equals b where f and g are continuous functions and f of x is greater than or equal to g of x for all x in AB is the area is equal to a to b of f of x minus g of x, all integrated with respect to x. Okay. So there's your magic formula. Okay, now this assumes that f of x is always greater than g of x. Okay. Okay, if we have a drawing here, and I take a curve f of x, okay, and then I take another curve. Oops. Oh. There we go. Okay, and I take another curve, say g of x. Okay, and the boundary of this curve goes from A to B for both of the curves. You can see that f of x is always greater than g of x, regardless of where it is on the curve. Okay, so if this is true, then the area is just the integral of f of x minus g of x, and that gives me the area. It gives me the area in between these two. Okay, in between the two curves. This is what we would call A, the area A. Okay. Okay, so let's do an example. Find the area of the region bounded by y equals x squared plus 1 and y equals x from 0 to 1. Okay. So let's draw a picture and see what's happening here. All right. Okay. And so first we need to see, okay, which one's on top. Okay, we can either do this algebraically or we can do it graphically. Okay. But we're looking at 0 to 1, right? So if we look at this graphically, Okay. When x is 0, we're here. When x is 1, we're here. Okay. So,
Sorry, never mind.
when x is 0, we're right here. When x is 1, we're right here. And so we need to say, well, what's happening with these functions? Well, no matter what I plug in, what I let x be, x squared plus 1 is always going to be bigger than x, right? If I just let x be, say, 1/2, then I square that and I add 1, that's always going to be bigger than the fraction. Whatever a fraction squared is, plus 1 is always going to be bigger than the original fraction. Okay, so we could say that x squared plus 1 is always greater than or equal to x, okay, for all x between, for all x in 0, 1. We use this e as an element. So it's an element of that set of numbers that from 0 to 1, that region from 0 to 1. So for all the values, that one is bigger. So we know that x squared is going to be on top. So what is that? Why is that important? Well, that's important because this is then going to be my f of x. And this is going to be my g of x. Okay, I need to know which one's on top and which one's on bottom, which one's greater and which one's smaller, so that I subtract in the correct order. If I get the order of subtraction wrong, I get the integral wrong. Okay. Okay, graphically, we could see this pretty easily. If I graph x squared plus 1, what does x squared plus 1 look like? It's definitely a parabola, and it has a y-intercept at 1. Okay, so we have a parabola, and maybe I'll move this down. We have more room to draw. So I have more room to draw my parabola. Okay, so I have a parabola. Okay, so we have this parabola here, that's x squared plus 1. Okay, and then we have this line y equals x. Well, that's just the line that goes through the origin and makes a 45-degree angle. Okay, that's y equals x. Okay, and so from 0 to 1, my parabola didn't go up very far enough, but okay, that should be at 2. We'll make the parabola a little wider. Okay, there we go. Okay. And so what's the region that I want? The region that I want is this region here. Okay, so it's going to be f of x minus g of x. So we want the area between that. What are we basically doing? Okay, in finding this area, is we're basically finding the area. If I get rid of this line, we're basically finding the area underneath the first one, right? Underneath the first curve of the parabola, and then I'm subtracting off. If I go and find the area under the second one, the second curve, this would be the area under the second curve. And what am I doing? I'm just subtracting off that area. I don't know why it's not keeping my scribble. Okay. Oh my gosh. Heck is the problem? Lovely. that again. Okay, scribble, 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 scribble. Okay, good. Okay, and so we're subtracting the area underneath the second curve from the area underneath. Oh, if I scribble it erases. Okay, thank you. Thank you, Samantha. You can be my OneNote expert. I'd like to get my, eventually I'm going to figure out how to get my toolbar back in OneNote. I did know how to do it in OneNote 10, but not OneNote 11, Windows 11. So supposedly there's a toolbar that I can get, but whatever, doesn't matter. Okay. Okay, so that's the big idea. So let's go ahead and do the math. Okay, the integral from 0 to 1, the area is equal to the integral from 0 to 1 of f of x minus g of x. Okay, or x squared plus 1 minus x dx. Okay, so this is equal to a 0 to 1. I'm just going to distribute the x. I'm going to go x squared minus x plus 1 dx. Okay, now I'm going to integrate term by term. And this becomes x cubed over 3 minus x squared over 2 plus x evaluated from 0 to 1. Okay, I'm going to plug in 1, and I'm going to get 1 cubed over 3 minus 1 squared over 2 plus 1 minus, and then I'm going to plug in 0. 0 cubed over 3 minus 0 squared over 2 plus 0. Okay, all the zeros go to 0, so they're gone. And over here, I'm left with 1/3 minus 1/2 plus 1. If I combine the negative 1/2 and the 1, okay, I get 1/2. And everybody knows that 1/3 plus 1/2 equals 5/6. So the area is 5/6. Okay, let's go over another example. Second example. Okay, number 2. Find the area.
Professor, could you scroll up a little bit? Sorry about that.
Roll down, you mean?
Oh yeah, right there's good. Sorry.
Okay. Okay, find the area enclosed by the parabolas Okay, find the area enclosed by the parabolas. Y equals x squared and y equals 2x minus x squared. Okay, so we have a couple issues here. One, we don't know where this is defined, on what interval. Okay, is this defined? And two, we don't know which one's on top and which one's on bottom. So we got to solve both of those issues before we can even write the integral. Okay, so where do I know that this is enclosed area? Well, it's between where they intersect. Well, where do they intersect? Where does this function and this function intersect? How can I figure that out?
Set them equal each other.
Yeah, thank you, Con. Yeah, set them equal to each other and solve for x. Solve for the values of x where they're equal, and then I can go back and figure out what those values represent for y, and those will be points of intersection. Okay, thank you. Okay, so we have x squared is equal to 2x minus x squared. Okay, I'm going to add x squared to both sides. And I get 2x squared is equal to 2x. Okay, now I have a choice to make here. Okay, I can either do this algebraically accurately, or I can mess up and eliminate one of my solutions. Okay. You might be inclined to do this, and this is wrong. Does anybody know why this is wrong? Why I can't divide by x?
First, x may be equals 0.
Yes, very good, Ling. Absolutely. Okay. Okay. X, you'd have to assume that x is not equal to 0, and x could be 0. And we all know that division by 0 is undefined in mathematics. Okay, so we don't want to divide by x because we could end up inadvertently dividing by 0. It's bad. So instead of doing that, what are we going to do? We're going to toss this to the other side. And everybody knows that when you toss something across an equal sign, it becomes negative. And then we're going to do the F word. And there's 2 F words in math that nobody likes to do. No algebra students like to do. The first F word is in arithmetic, and that's called fractions. Nobody likes fractions. Everybody hates them. They run out of the room screaming every time I try to do a fraction. Okay, the other F word is you find in algebra, and that's factor. Nobody likes to factor. Okay, and then the other F word that nobody likes is you occur in calculus, and that's factorials. Nobody likes to deal with factorials. Okay, so a lot of F words in math that people don't like. I'm going to factor out a 2x, and that gives me x minus 1 is equal to 0. Okay, setting both of these equal to 0 will give me the solutions. And so I'll say that 2x could equal 0, or x minus 1 could equal 0. And so x could equal 0, or x could equal 1. Okay, so I get 2 solutions here. X equals 0 or x equals 1. Okay, so how does that translate back to my original functions? Well, if I plug in 0 into either of these functions, I get 0. So we know that when x is 0, y is 0, and that creates a point 0, 0. Okay, that's my first point of intersection. Okay, it's at the origin. Okay, and who loves origins? Owls love origins. Yeah. Okay. Okay, that's my origin joke there. Okay, these are the jokes, people. Okay, just go with it. Okay, so that's my little friend, Mr. Owl Origin. Okay, and so we're at the origin, or when x is equal to 1, y is equal to 1. Okay, you can plug into either of them, and so this becomes 1, 1. Okay, so we have 0, 0 as a point of intersection. Okay, or 1, 1. And I go POI as point of intersection. Okay, it's not to be confused with poi, which is a lovely Hawaiian delicacy. Okay, okay, point of intersection here, 0, 0, 1, 1. Okay, so we know that x is going to go from 0 to 1, right? So those are the limits of integration. We found the limits. Now we have to figure out where is which equation's on top and which equation's on bottom. Okay, it might be easiest to see that by graphing these things. We know what y equals x squared looks like. That's this guy here. Okay, we don't necessarily know what y equals 2x minus x squared looks like. However, if I rewrote it as negative x squared plus 2x, okay, I know that a couple of things about my equation here. It's a parabola, and it's a negative parabola, which means it's upside down. Okay, I also know that this thing goes through 0, 0, and 1, 1. Okay, from my points of intersection, I know this goes through 0, 0, and 1, 1. Okay, I know it's an upside down parabola as well. I also know where the vertex is, because if I write it like this is A, B, C. And I know that the vertex, the x coordinate of vertex, is at negative b over a. And if I take this, down here, this should be a negative 2. I'm sorry, I miswrote that. Okay, this should be a negative 2x. Okay, if I take negative b over a, okay, I get negative 2 over negative 2, which is 1. Okay, and so 1 is the x value, and so the vertex would be here at 1, 1. Okay, where x is equal to 1. That's the vertex of that parabola. And so if that's the vertex, that's going to be the highest point because it's an upside down parabola, and it's going to look like this. And so what's the area that I'm looking for? Well, I'm looking for that area there. Okay. And so which one is on top? What's my f of x in this case? Well, my f of x is this guy. That's the one that's on top. What's my g of x? G of x is my x squared. That's the one that's on bottom. G of x. Okay. So now we have all the components we need to write the equation, write the integral.
Professor,
Yes.
I think you are wrong about the vertex of the parabola. It's negative b over 2a. You
Oh,
forgot the
2a.
number.
Thank you. Thank you. Yes, 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 yes.
Oh my God.
So how did I mess up here?
I think you added the 2 is what messed it up.
Yeah, I added the 2. Okay, thank you. Thank you, thank you, thank you. Yeah, it was this. I had it correct in my notes, sorry. Yeah, so adding the 2, it should be, yeah, it should, I knew that I was missing a 2, so I was like, where did that 2 go? So thank you for that, negative b over 2a. Okay, so 2x squared, or negative x squared, so negative x squared plus 2x plus 0, there we go. Okay, so it's negative 2 over negative 2, thank you. Okay, which is still 1. Okay, thank you so much. Okay, perfect. Okay, so the area is going to be equal to 0 to 1, okay, of f of x, which is my 2x minus x squared, minus g of x, which is my x squared. Okay, dx. Okay, so this becomes integral 0 to 1 of 2x minus 2x squared dx. Okay, so this becomes 2x squared over 2 minus 2x cubed over 3, evaluated from 0 to 1. So this is the 2's cancel here, and that becomes 1 squared minus 2 times 1 cubed over 3, minus 0 squared minus 2 times 0 cubed over 3. Okay, again, this thing goes to 0, right? And so this is just 1 minus 2/3, which is 1/3. Okay.
Here's one.
Yeah.
Why you bug me? You know I got class.
I'm gonna mute you. Sekla, you're unmuted, so I'm gonna mute you.
Professor, could you go back up again? Thank you.
Professor, I have an idea.
Yes,
So for you, for you, like you, the way you, your solution is like you you create a graph to see what functions is on the top and what function is on in the bottom.
right.
But can I choose like algebraically from? I know we are seeing from 0 to 1. So can I choose like a number between 0 and 1 and then
Sure,
and then
sure, yeah.
substitute into the functions and then we will see which value is bigger. So that's one is on the top. You understand what I'm talking?
Yeah, that works really well if you know the behavior of the function between, as long as there's not multiple intersections. Okay, and we're actually, that's a great segue into the next problem, because in the next problem, there are multiple intersections. And so you might get, if you have 2 or 3 points where these cross, you might get a function to be on top that is on bottom. So I wouldn't just look at the whole interval and choose one value. You would have to break up all of the intervals into smaller intervals if they cross multiple times, smaller intervals, and then you could test each of those subintervals. Does that make sense?
Yes, thank you.
Okay, so again, that's a great segue into the next solution, next example here. So number 3, find the area of the region bounded by the curves y equals sine x and y equals cosine x from 0 to pi over 2. Okay. Okay. So what's the problem with 0 to pi over 2? Okay, if I were to test a value, let's think about Kahn's suggestion here. If I were to test a value between 0 and pi over 2, let's say pi over 4 or pi over 8 or anything like that, okay, we would see that sometimes sine is bigger and sometimes cosine is bigger. Okay, it depends on where I'm at. So that so that's kind of weird, right? So let's just plug in the endpoints here real quick. Okay, if I take the sine of 0, that's 0. If I take the cosine of 0, that's 1. So at some point, the sine is 0, sine of 0 is 0, okay, and the cosine of 0 is 1. Okay, interesting. So this is the cos, and this is the sin. Okay, but at pi over 2, what happens? The sine of pi over 2 is 1, and the cosine of pi over 2 is 1. Now here, this is the sine, and down here, this is the cosine. So what happened? They swapped places, right? Where did they swap places? Well, where did they intersect? Where is sine equal to cosine? In the first quadrant.
Pi over 4.
Power.
Yeah, thank you, Eric. Thank you, Jermaine. Yeah, pi over 4. So at pi over 4, they're going to switch positions, right? So the sine, okay, which would have looked like this, is coming out here. And the cosine, which looks like this, is coming out here. And then I didn't line that up too well, but right here at pi over 4, I'm just going to make it bigger. Okay. That's where they intersect. Does that make sense? So what do I do here? Since one is on top and one is on bottom, okay, up to pi over 4, I'm going to break this up into 2 different integrals. Okay, so I'm going to have 2 different areas. I'm going to calculate this first area. Okay, and then I'm going to calculate this second area. And then I'm going to add those 2 areas together. Okay.
Professor,
Yes.
can you do it from 0 to pi 4 and then you times 2? Is it correct?
Possibly because of the symmetry involved, it might be. But there's no guarantee that it will be. It's possible in this specific case that that could work. However, it may not be the case. Does that make sense?
Yes, thank you.
Because if I had a, you know, a function, maybe a cubic, that went like this, and then I had, you know, something else that went like that. Okay, say I had 2 cubics. There really isn't much symmetry to work with. Does that make sense?
Yes,
This would
thank
go
you.
down eventually. Okay, so I have a cubic and a cubic, and you know, one is, it's kind of hard to see because they're the same color. But if I have a cubic and a cubic, okay, there really isn't going to be, it depends on where those cubics live, depends on the symmetry involved. Okay, and I could have chosen a different cutoff point. I could have said that it's instead of 0 to pi over 2, it's, you know, pi over 8 to pi over 2. Right, I could have started, I didn't have to start at 0. Okay. Okay, so just be careful of that. Okay, good questions though. Okay. Okay, so how are we going to set this up? We're going to set this up as from 0 to pi over 4. Okay, from 0 to pi over 4, we're going to start with the one on top. Well, what's the one on top from 0 to pi over 4?
Cosine.
Cosine, thank you. Cosine, and then the one on bottom is obviously sine. Dx. Plus, we're going to set up the second one. This is going to be pi over 4 to pi over 2. And this is going to be sine is going to be on top. And then cosine's on the bottom. Right? Okay. Okay, now we're going to integrate. What's the integral of cosine?
Negative sign.
No, I don't think so. The integral.
Sine x.
It's sine, it's positive sine. You're going backwards, right? The derivative of sine is cosine. So the integral of cosine is just positive sine. You're going backwards. So sine x minus, and what's the integral of sine x?
Cosine x.
It's negative cosine x. Okay, evaluated from 0 to pi over 4. Okay, plus the integral of sine x, negative cosine x, minus the integral of cosine x, which is just sine x. from pi over 4 to pi over 2. Okay, so now I'm going to plug in my limits of integration. Okay, and so I get the sine of pi over 4 plus these two negatives make a positive plus the cosine of pi over 4. Okay, minus the sine of 0 plus the cosine of 0. Now the sine of 0 and cosine 0, they're not 0. Okay, only one of them is. So don't make the mistake of canceling this out and saying, oh, this cancels out because they go to 0. No, the cosine of 0 is 1, not 0. So don't make that mistake. Okay, so we got this guy plus, okay, now plug in a pi over 2. This is going to be negative cosine pi over 2 minus the sine of pi over 2 minus the negative cosine of pi over 4 minus the sine of pi over 4. Okay. Okay, what is the sine of pi over 4? Well, it's the same as the cosine of pi over 4. It's radical 2 over 2. So this is radical 2 over 2 plus radical 2 over 2 minus the sine of 0, which is 0, plus cosine of 0, which is 1. Okay, plus the negative cosine of pi over 2. What's the cosine of 90 degrees? 0. What's negative of 0? Well, it's just negative 0. Just 0. Okay, negative of 0 is 0. Okay, minus the sine of pi over 2. What's the sine of pi over 2? It's 1. Okay, minus, okay, the negative of cosine of pi over 4, that's radical 2 over 2. Minus the sine, which is radical 2 over 2. Sine of pi over 4, which is radical 2 over 2. Okay. Okay, so we have radical 2 over 2 plus radical 2 over 2. So that's just radical 2. That's 2 radical 2's over 2, which is just radical 2. Minus 1 over there. And then we have a minus 1 over here. And then we have negative radical 2 over 2 minus radical 2 over that's going to be negative radical 2. But then I have a minus, so that's a minus negative radical 2. And so that's just going to be plus radical 2. Okay, so you are right, Con, by symmetry, the left side is the same area as the right side. But will that always be the case? No.
Professor, so the area is equal to rad 2 minus 2, right?
Yes, correct. So this is 2 rad 2 minus 2. Okay, so we're gonna spice things up. We're gonna do one final example here. Okay, we're gonna spice it up and we're gonna use what's called a y-oriented function. Okay, y-oriented function instead of an x-oriented function. Okay, number 4. Find the area enclosed by the line y equals x minus 1 and the parabola y squared equals 2x plus 6. Right? Okay, so what we're gonna have to do, because this guy here is a function of y. It's not a function of x. If I tried to solve this for y, I would end up with two separate functions. Okay, this really is a function of y, and I can solve the equations so that they are functions of y instead of functions of x. Okay, so solve for functions of y, where that's the independent variable. Okay, and x is the dependent variable. Right? Okay, so let's solve for x. Okay, make these functions of y. So in the first one, we have y equals x minus 1. So I want to solve for x. So I'm just going to add 1 to both sides. And I get x equals y plus 1. So that's my first function. Okay, my first f of y or g of y. Okay, I don't know which it is yet, if it's f of y or g of y, and how that goes into helping me find the area between these two curves. But we have it solved in terms of y. Okay. Okay, and let's do the second one, which is the y squared plus 2x is equals 2x plus 6. Okay. And so subtract the 6, divide by 2. Okay, and we get x equals 1/2 y squared plus 3, right? Sorry, minus 3. Okay. Okay, so we're saying that we want an area that's enclosed, right? Enclosed between these two. Okay. So I need to know what the points of intersection of these are. So let's just set them equal to each other and solve for y. Okay, so y equals 1, or sorry, y plus 1 is equal to 1/2 x y squared minus 3. Okay, I can toss everything to the other side, or if I toss, if I can keep the 1/2 positive, maybe I'll just subtract y and subtract 1. Minus y minus 1. I get 0 is equal to 1/2 y squared. Okay, minus y minus 4. Okay, that equals 0. I can get rid of the 1/2 that's in front by multiplying everything through by 2. Maybe I'll do that. So 0 is equal to y squared minus 2y minus 8. Okay, I could factor this now. This becomes y minus 4 times y plus 2 is equal to 0 after I factor it. So that tells me that y is equal to 4 and y is equal to negative 2. Maybe I'll put the negative 2 first. Y equals negative 2. Okay, and y equals 4. Okay, so two solutions. Okay, so where are my points of intersection? Well, I can plug these values back into either of these equations and it should give me the same result. That was the whole point of doing this. Okay, so if I plug in negative 2 into the top equation, okay, I get negative 1. So when y is negative 2, x is negative 1. So we get a point of intersection at negative 1, negative 2. If I plug in 4 in for y, I get 5. And so I get x equals 5, and so this is a point of intersection of 5, 4. Okay, so I have my points of intersection. Okay. And I know what y goes from. Y goes from -2 to 4, because again, these are functions of y. So -2 is less than or equal to y, which is less than or equal to 4. Okay. So for a y-oriented function, the area is equal to c to d. We don't use a and b, we use c and d because they're y-oriented. Okay, f of y minus g of y dy. Okay. But we got to know which one's on top and which one's on bottom. Okay, basically in a y-oriented graph, what we're really asking ourselves is which one's most positive? Which one's bigger? And when we talk about bigger, it's which one's most positive? Which one's least positive? Okay, now they can both be positive. It doesn't matter if they're both in the positive or in the negative, whatever. But I want to know which one's the most positive, which one is furthest to the right. Okay. Which one is furthest to the right, and that's going to be the one that is most positive. Okay, in a y-oriented graph. Okay, so let's graph these guys. Okay, and see what happens. Okay, x equals y plus 1. That's the easier one to graph. Okay, x equals y plus 1. Okay, that one is going to be basically y equals x minus 1. So y-intercept of -1, and then a slope of 1. Okay, and so we get, oops, I draw that better. Maybe I'll use a ruler. Is there a ruler? Ruler? No. Ruler? No. I just upgraded everything, so now I don't know what I'm doing. Okay, ruler? Nope. No ruler. I'll find it this week sometime. Okay, where the heck is my book? Whatever. Okay, we'll just freehand this as best as we can. There we go. Yeah, of course. Scribble means erase. That's lovely. No, it doesn't. Come back. There we go. Okay. Fun time. Okay, so we have that guy, which is x equals y plus 1. Okay, we know that this goes through point -1, -2. Okay, these points here. This point here and this point here. It goes through those 2 points. Both of these graphs have to go through these 2 points. Okay, so at -1, -2, I'm down here. I'm going to enlarge that point. -1. Okay, -1, -2. Okay, is there. -1, -2. Okay, whatever. And then the other one's going to be at what, 5, 4? So 1, 2. I got to make these points closer together. Okay, 1, 2, 3, 4, 5, and then it's gonna be way up here. Okay. Two, 3, 4, 5. 1, 2, 3, 4, 5. We're gonna get there. No, it's not there. It's here. It's there. Okay, there we go. And out 5, up 4. Perfect. Okay, so that's those 2 points of intersection. Now, what does the parabola look like? Well, the vertex of the parabola, I'm not going to go, I'm not going to solve for the vertex of the parabola, but if we look at this, there is no B, okay, for this guy here, there's no B. A is 1/2, and B is 0, and -3 is C, okay? So when B is 0, that negative B over 2A, okay, y is equal to negative B over 2A this time, okay, that's going to be 0. So it's going to be y equals 0, okay, and if I plug in 0 for y, I get x equals -3. So my vertex ends up being at -3, 0. That's my vertex. Okay, looking at that parabola. Okay, so if I go out here, 3, okay, there's my vertex. And what I get is I get a parabola that looks like this. That was pretty close. Okay.
Could you scroll back up for a second, Professor?
Okay.
Back to the vertex.
The
I'll just take a picture of it.
Okay.
Yeah, thank you.
Okay.
You can go back now. Thank you.
I can put in a little bit. No matter what it is, it's going to go to 0. Okay. Okay, so this is, what's the area that we're looking for? It's this area here. That's the area we're looking for. Okay, and so using this formula, okay, using that formula, what is C and D? Well, that it's with respect to y. This is a y-oriented, this is with respect to y, right? So this is -2 to 4. Okay, now what's f of y? Which one of these functions, okay, which one of these functions, x equals y plus 1, okay, which is this one, or x equals 1/2 y squared minus 3, which is this guy. Okay, which one of those is most positive for all the values of y between -2 and 4? Which one is furthest right?
X equals y plus 1.
Yeah. So this is going to be my f of y. And this is going to be my g of y. So it's y plus 1 minus 1/2 y squared minus 3 dy. Okay, so now I'm
Wait,
gonna
Professor, can you explain that one more time, please?
sure. So we want the function that's most positive. Okay, it has the biggest, think of the biggest absolute value, or not absolute value, the biggest value on a number line, right? So if I do some slices here, okay, let me do a slice. Okay, let me do a horizontal slice. So say I'm at, I don't know, a y value of 1, right? And I do a slice. Let me do a different color. Let me do a slice right here. Okay, I take this as my vertical slice, right? As my rectangle. That's kind of what we do when we're talking about integrals, is we're summing up an infinite number of rectangles, right? So if I take my slice here, okay, which one is the bigger value on a number line? The bigger values are always to the right. So no matter where I'm at between these two, between -2 and 4, the bigger values are always going to be along this function. So that's my f of y. No matter where I take my slice, x equals y plus 1 will always be on the right. And that's the bigger function. Okay, that's the bigger value at that point. This has a value of 2, where over here, this one has a value of, say, I don't know, whatever, 2 and 2.5. Who knows? -2 and 1/2. Okay, but it doesn't matter where I take my slices, my horizontal slices. Okay, because really what I'm doing is I'm summing up an infinite number of slices. Okay. I don't know if that helped or if it confused you more, but that's the idea. Okay. Is we want it to be the one on the right, the bigger one.
Makes sense. Thank you.
Okay. Okay, so I'm going to distribute my negative sign. And I get -1/2 y squared, okay, plus 3 plus y plus 1. Okay, integrate from -2 to 4 dy. Okay, and so I get -1/2 y squared plus y plus 4 dy integrated from -2 to 4. Okay, so let's integrate term by term. So this is -1/2 y cubed over 3 plus y squared over 2 plus 4 y from -2 to 4. Okay. So this becomes -1/6 times 4 cubed plus 1/2 times 4 squared plus 4 times 4 minus -1/6 times -2 cubed plus -2 squared over 2. Okay. Plus 4 times -2. Okay, so 4 cubed, that's 64 over 6. So this is -64 over 6. 4 squared is 16 divided by 2, that's 8. 4 times 4 is 16. Okay, minus. Okay, this is going to become -2 times -2 times -2, that's 8. So this is going to be -8 times negative. Okay, and then this is going to be -2 times -2, which is 4. 4 squared divided by 2 is 2. Plus 2. And then this is going to be -8. I'm going to distribute that negative sign. So this is negative 64.6 plus 8 plus 16 minus 8.6 minus 2 plus 8. So this is going to become negative 64.6 plus negative 8.6 is negative 72.6, which is just negative 12. Okay, plus 8 plus 16, that's 24. Minus 2 and 8 is just 6, right? So this is negative 12 plus 30, which is 18. And that's the solution. Okay, so we get, it's kind of interesting, we get whole number of units for the area between these two curves. That whole area is 18 whole units.
Professor.
Yeah.
Okay. So you draw a graph to find which function is bigger than the other one, but however, like you find a vertex, but can I
Right.
use that? Can I use Desmos to draw the graph? Can I use Desmos on the exam and the quiz? You know
Yeah,
Desmos.
I mean, you can use Desmos, that's fine.
Okay, thank you.
Okay, you can also just test a point. You know, if you know it's between the two and they don't intersect, then you could just take, you know, your value of 0 for y and see which one's where. Okay, you could do it algebraically as well. You could say, okay, what at y equals 0, okay, then x is equal to 1, right? For your first for, you know, x equals y plus 1, and x is equal to negative 3 for x equals negative 1/2 y squared minus 3, right? Or it's just 1/2 y squared minus 3. Why it's not moving? Okay, for x equals 1/2 y squared minus 3.
Professor?
So you could just say, hey, this one's bigger, and they don't intersect, so you could do it algebraically. Yeah, Eric?
Professor, I have a question. Is 1/2 y squared the same as y squared over 2?
1/2, yeah, it's the same thing.
Okay, because I did the math, but I got 42 because I kept the y squared over 2, which would just made it y cubed over 3. And I see that you got negative 1/6.
Yeah, because there was already a negative 1/2 in front of it, right?
Yeah, but since it's the same thing as y squared over 2, wouldn't that just be y cubed over 3?
Yeah, but I have this constant in front.
Okay. All right, I just messed up then.
Okay. I mean, I understand
Question.
what you're saying, but you know, if we had a 3 here, then they would cancel.
Yes, correct.
I mean, not a 3. If we had a 3 here, then they would cancel.
Mhm.
But that's not the case.
All right, thanks.
I mean,
I had a question about the areas when the axis is, or when the graph sits below the axis, just like in this case where it's to the left, so you have
yeah,
negative x values.
yeah. It
So
works
that
out the
doesn't
same.
change.
No, it doesn't change.
Okay.
It works out exactly the same. Because what we end up actually adding the areas, because what we end up doing is we end up going like this, f of y minus negative g of y. And we end up actually adding the areas together.
Okay.
It's a good question. But yeah, it doesn't affect it at all. Okay, that's it for your first lesson. If you have questions, you can stick around. Otherwise, you are free to go.